To initiate our discussion of thermodynamics, I think it pertinent that we first introduce two processes that are integral to any chemical engineer's trajectory in their career path. These two processes are two manipulations of some sort of system with a movable boundary, and inside that system is going to contain some sort of ideal gas. Now, in these two systems, we are going to derive expressions for their pressure volume and pressure temperature relationships based upon the first law of thermodynamics. And what this first law says is that internal energy is equal to heat added or removed from the system minus the work done by the system, or the work done on the surroundings. And that's what this PV term, pressure volume term, is right here. That's the work done by the system. And you can see that that sign is negative because the work is going to be done on the surroundings. The work is leaving the system. So this is, again, the first law of thermodynamics. I'll abbreviate it LOT there. And what is definitely most done generally to this expression is that the differential of both sides is taken, and when pressure is constant, or you have some sort of reversible process in which the pressure of the surroundings is equal to the pressure inside the system, you will then derive this expression here. Now, again, this is for any sort of reversible process, which is what we're mainly going to be dealing with here. Reversible. What does reversible mean? It means that the pressure of the external environment, or P external, is going to be equal to the pressure inside the system. Wonderful. So now, given these two terms, let's go ahead and define two processes that we can do on systems here. So first, I'm going to have some sort of container, and again, we're going to have some sort of movable boundary, for example, a piston, and inside we have some sort of ideal gas, right? Now, for this system, let's say we want to manipulate it isothermally. And we also would like to do that reversibly. As you may guess, or if you weren't already aware, isothermally means we are going to hold temperature constant. And again, we just defined reversibly as the pressure of the surroundings being equal to the pressure inside the system itself. So with these two kind of definitions out of the way, we can talk about either an isothermal expansion, in which the volume will grow, or an isothermal compression, in which the volume will shrink over the course of the process. Now, whether we expand or contract it, we are still going to derive very similar equations, and in this sense, I will call our initial volume V initial, and our final volume V final. In future videos, you may see me derive this as V1 and V2 for the sole reason that the processes, we may not be only doing one process on the system, such as in an engine. Now, I'm also going to denote our initial temperatures as Ti and Tf, as well as our initial pressures. Now, obviously, in this isothermal case, we are not going to have any change in temperature. So, starting at this first law differential here, we can then say that du, or the differential of internal energy, is actually equal to the specific heat at a constant volume times the differential in temperature. And that's going to, again, be equal to our differential of heat added times our work done by the system term there. Now, we've defined this as an isothermal system, and what that means is that there's going to be no change in temperature, or dT is going to be equal to 0, which will then make this entire side, left-hand side of our equation here, equal to 0. So we can rewrite this expression for an isothermal reversible process as follows. the heat is going to be equal to the work done by the system. Now this is a pretty important relation that I would say is almost worth committing to memory. Now that we've gone ahead and done this, we have also defined this as a reversible process. What this means is that the pressure external is the pressure of the system. Now, that also means that since we're dealing with an ideal gas, the pressure is going to be equal to RT over V, where V is some sort of specific volume term. So let's go ahead and throw that in this expression as well. Again, that comes from the fact that we're doing this reversibly. Now, we only have one changing variable in this right-hand side of the equation now, and that is going to be volume. So we can go ahead and integrate both sides. And now the importance, we can bring RT outside of the integral as the constant temperature, as well as the gas constant are both going to be constants. And now we have come up with this relationship. So we have some sort of integral that we want to find here, and we need to go ahead and define some bounds for this expression. Now the volume one is going to be quite simple, right? We want to go from our initial volume all the way to our final volume. And for the heat, this may be a little bit more difficult. However, what we are trying to define here is some sort of relationship between the heat and the volume of the system. And so we can go ahead and set it at, we'll start our initial heat at 0. We have 0 heat added at the initial state. And then we want to go ahead and define some sort of Q, or final heat added to the system. I'm going to go ahead and call this Q reversible, since it's for a reversible isothermal process. Now, integrating both sides, we will be left with the following. Let's see, ln of F minus natural log of initial volume. With this relationship, we can go ahead and use our logarithmic rules to write Q reversible as being related to gas constant times the temperature times the natural log of the final volume over the initial volume. And this is the expression that we were attempting to derive here. We've now derived some expression of what heat we need to add or remove from a system isothermally, or isothermally compressed or expanded reversibly, in order to change its volume by some amount. What this expression tells us is that if, let's say, Vf is greater than Vi, as would be in the case in some sort of expansion, right? Then this ln term is going to be positive, and heat must be added in order to expand. Similarly, if Vf is less than Vi, or we've compressed the system, we must remove heat. So that is our expressions here for our isothermal reversible expansions and compressions. However, let's say we instead want to do the same thing except this time we want to do it adiabatically. And we'll still do it reversibly as well. So we want to do another expansion or compression, but this time we're doing it adiabatically or reversibly. I'll go ahead and copy down our first law expressions here. There we are. Now, For an adiabatic process, we are assuming the system is perfectly insulated. So that means that we will have no change in heat for our system here. Therefore, we can write the relation that the specific heat at a constant volume times the differential of temperature is going to be equal to the work done by the system. Now, with this relation here, we can again, since we're using the process reversibly, replace P with RT over V. However, what's different in this expression is that now temperature can potentially change. Remember, heat and temperature are not synonymous with one another. Therefore, we want to do some sort of separation of variables in order to solve this differential equation. So, let's divide both sides by T and integrate. Our specific heat with a constant volume will be a constant. And we can just integrate from our initial temperature to our final temperature, and from our initial volume to our final volume. This relationship, then, is going to be fairly easy to solve. Again, I'm going to skip the step of our log rules. So, this differential will be the final temperature over the initial temperature. And I'm going to go ahead and take out this negative sign here as well, and just flip the terms of the log. So, we'll say R times the natural log of initial volume over final volume. With this relationship then, if we want to simplify it a little bit, I suppose we could divide both sides by R. And finally, we can then raise both sides to the power E in order to remove our natural logs here. And now we have defined some relationship between our changing temperature and changing volume to some sort of exponential constant, based on the specific heat of whichever gas substance we are manipulating. However, I think it pertinent that we go a little bit further in this definition, and we attempt to derive some sort of expression to relate the pressure and the volume to one another, as this is where it gets particularly interesting. So, again, we know this is some sort of ideal gas being done reversibly, so we can relate our temperature to our pressure and volume via the ideal gas law. So, let's go ahead and do this then. If I divide a temperature by a temperature, I'll go ahead and say this is TF, and then TI would be the initial pressure, the initial volume over the gas constant. If I divide these two by one another, this gas constant is going to cancel, and I will be left with this expression here. There we are. Distributing the exponent, will result in this expression. And then, finally, by some sort of cross multiplication, we can come across that Pi CV over R. Let's see. And then we will do VI. I'm doing this cross multiplication first. So that's going to be CV over R plus 1. Now, I could keep the exponent as that, however, I am going to instead rewrite this as CV plus R over R, which is exactly identical to one another. I multiplied the 1 by R over R. And then the other side will be something that looks very, very similar. And then, from the definition of enthalpy, we have that the specific heat plus the gas constant is the specific heat at a constant pressure. So, we can again rewrite this as follows. And you know what? I'm actually just going to rewrite this up here. There we are. Now, from this expression, if we raise both sides of our equation here to the R power, and then simplify our exponents, we will be left with oops. This should have been a final volume here, not an initial volume. Now, we can basically, now we can state that at any point during the process, this adiabatic compression or expansion, the volume signs and the pressure signs, these guys are now irrelevant for this expression, because we can now write that PV times this exponent here, this relation, is going to be some sort of constant. Which means that at any point during this process here, this relation will always be a constant, which is quite fascinating, and we will dive in further in our next video to try and apply these two expressions to some sort of applicatory scenario in which we will attempt to derive Bernoulli's equation. Thanks for watching.